Quantum mechanics governs atoms. General relativity governs galaxies. Both work flawlessly, each on its own territory. But at the center of a black hole, both territories merge. Matter is compressed to quantum scales while gravity reaches infinity. The equations of one theory begin to contradict the equations of the other. The result is not an answer. The result is an infinity that means, here, physics breaks. Everything else in the universe follows quantum mechanics. Light, electricity, the nuclear reactions that power the sun, the chemical bonds that hold your body together. Every interaction we have ever measured, cataloged, and predicted with astonishing precision, all of it is quantum, all of it except gravity. Gravity sits alone, described by Einstein's general relativity, a magnificent theory in its own right, but one that speaks an entirely different language. And no one in a century of trying has managed to teach these two theories to talk to each other, to understand why this matters, why it is not just a technical irritant, but a genuine wound in our picture of reality. We need to go back to the beginning, not the beginning of the universe, though we will get there. The beginning of our understanding. The world, as it turns out, is made of a surprisingly short list of ingredients. At the smallest scales we can reach with our instruments, matter comes down to a handful of fundamental particles, objects with no detectable internal structure, no smaller pieces, no seams you could pull apart, electrons, quarks, neutrinos, a few others, and alongside the particles of matter, there are the particles that carry forces between them. This is the picture that took a century to assemble, and it is one of the greatest intellectual achievements in human history. We call it the Standard Model, and it is both a triumph and a confession of ignorance, because for all its power, it says nothing about gravity at the quantum level. But let us not rush to the edges. Let us start where all good stories start, with what we can actually see. Pick up a glass of water. You are holding something made of atoms. Inside each atom, a nucleus surrounded by electrons. Inside each nucleus, protons and neutrons. Inside each proton and neutron, quarks bound together in tight, furious clusters. Go deeper than that, and we currently find nothing. The quarks and electrons appear to be points, fundamental, indivisible, at least for now. What keeps all of this together? What makes one particle care about another? The answer is forces. And when you look carefully at the fundamental forces of nature, you find something remarkable. There are exactly 4 of them. Or, counting a 5th that we discovered more recently, 5. But let us take them one at a time. Gravity. You know it. It is the one that keeps your feet on the ground, the one that shapes galaxies, the one that was puzzling Newton when the apple, legend or not, fell. Gravity is universal in the most absolute sense. Everything that has energy is subject to it, no exceptions. It has infinite range, falling off gently with distance but never quite reaching zero. It has one enormous flaw in the context of modern physics. It has never been observed to behave quantum mechanically. Every other force has yielded to quantum description. Gravity has not. There is something else strange about gravity. Every other force we know can be shielded. If you have a positive electric charge, negative charges will drift toward it and surround it, and from far away you see nothing, a neutral system, effectively invisible to the electromagnetic force. But gravity has no negative charges. Nothing anti-gravitates. Every particle, every photon, every neutrino contributes to the gravitational field in the same direction, which means gravity accumulates. It cannot be screened. Add more matter in one region, and gravity pulls more matter toward it, which strengthens the field, which pulls even more matter in. This runaway instability, this refusal to settle down into calm neutrality, is precisely why the universe is not a uniform fog of gas. It is why there are stars, why there are galaxies, why there is, eventually, us. The second fundamental force is electromagnetism. This one you interact with every moment of your life, even if you do not think of it that way. Every chemical reaction in your cells, in the food you eat, in the screen you might be reading this from, is electromagnetic. The rigidity of matter, the fact that you do not fall through your chair, is electromagnetic repulsion between electrons. Light itself is an electromagnetic wave. Electromagnetism is the workhorse of the cosmos, and we understand it better than any other force. The theoretical predictions of quantum electrodynamics, the quantum version of this force, have been confirmed by experiment to 11 decimal places. There is no other physical theory in the history of science that has been tested to anything remotely approaching that precision. To put it in scale, if you measured the distance from Moscow to Vladivostok using the predictions of quantum electrodynamics, your error would be smaller than the width of a human hair. Then there is the strong nuclear force. This is the glue that holds atomic nuclei together. Without it, every proton would repel every other proton and nuclei could not exist. Strong is the right word. It is by far the most powerful force at short distances. But it has a bizarre property that makes it unlike anything in everyday experience. The force between quarks grows stronger as they move apart. Pull two quarks away from each other, and instead of the force fading, as you might expect, it intensifies. It is as if the quarks were connected by a rubber band that stiffens as you stretch it. And conversely, when quarks are pressed very close together, they barely feel each other at all, a property physicists call asymptotic freedom. The strong force confines quarks permanently inside protons and neutrons. No one has ever observed a free quark. And here is one of the most counterintuitive facts in particle physics. The mass of a proton is not, in any meaningful sense, the sum of the masses of its quarks. The quarks inside a proton contribute only about 1% of the proton's mass. The rest comes from the energy of their interactions, from the furious churning of the strong force inside. E equals mc squared, working in the direction you usually forget about, energy becoming mass. When you step on a scale, roughly 99% of your weight comes not from the mass of quarks, but from the energy of the strong force binding them together. The weak nuclear force is the quiet one, the strangest one. It is responsible for a process called beta decay, where a neutron transforms into a proton, emitting an electron and a neutrino. This is what makes certain atoms radioactive. It is what powers certain nuclear reactors. It is what, in the sun, converts hydrogen to helium and keeps the star burning. The weak force has an extraordinary characteristic. It is the great destroyer. Almost every particle that is not absolutely stable will eventually decay through the weak interaction. The muon decays through it. Strange quarks decay through it. The entire second and third generations of the Standard Model exist at ordinary energies only as transient events, produced briefly in high-energy collisions and then dismantled, generation by generation, down to the stable first-generation residue that constitutes the matter we live in. But the most shocking property of the weak force is something else entirely. It breaks symmetry in a way that no other force does. The strong force looks the same, whether you mirror the universe left to right, or whether you replace all particles with their antiparticles. The electromagnetic force does the same, not the weak force. It distinguishes left from right. Neutrinos are left-handed. They always spin in the same direction relative to their motion. Antineutrinos are right-handed. This is not a convention. It is a fact about the universe. And the weak force treats matter and antimatter differently, at least slightly. That slight asymmetry, a few parts in a billion, is probably the reason why the Big Bang produced a universe with any matter in it at all, rather than equal parts matter and antimatter that would have annihilated into radiation, leaving nothing. You exist because the weak force is not perfectly symmetric. The implications of that are difficult to fully absorb. And then there is the fifth interaction, confirmed in 2012 at the Large Hadron Collider and celebrated with a Nobel Prize, the Higgs interaction. This is the mechanism by which particles acquire mass. The Higgs boson is the carrier of this force, and when it couples to an electron or a quark, it acts like a drag, a resistance to acceleration that we measure as mass. Different particles couple to the Higgs with different strengths, and that is why different particles have such wildly different masses. Why the lightest particle, the electron neutrino, differs from the heaviest known elementary particle, the top quark, by a factor of roughly 1 trillion. We measured those masses. We do not know why they take those values. This is the hierarchy problem, one of the deepest puzzles the Standard Model leaves unresolved, and it has motivated 30 years of theoretical speculation about physics beyond it. Now, you might ask, what does it mean for a force to exist? What is actually happening when one particle attracts or repels another across empty space? The quantum mechanical answer is both elegant and deeply strange. Forces are not fields in the classical sense, they are exchanges. When two electrons repel each other, they do it by throwing photons back and forth. Not the real observable photons of light, but virtual photons, quantum fluctuations borrowed briefly from the vacuum and returned before anyone can catch them. This is the quantum picture of electromagnetism. The strong force works by exchanging gluons, the weak force by exchanging W and Z bosons. Gravity, in theory, should work by exchanging gravitons, but no one has ever detected a graviton, and the theory of how gravitons should behave is mathematically pathological in ways that have resisted every attempt at repair. To understand why the exchange picture works at all, we need to talk about something at the core of quantum mechanics. The Heisenberg uncertainty principle. Imagine trying to locate an electron. You need to probe it with something, a photon perhaps. But the moment a photon hits the electron, it kicks it. The more precisely you try to pin down the electron's position, the more forcefully you must poke it, and the more violently its momentum is disturbed. This is not a technological limitation. You cannot build a better instrument to get around it. It is a fundamental property of the universe. Position and momentum cannot both be precisely defined simultaneously. They are genuinely uncertain in a way that has nothing to do with measurement errors. The same uncertainty exists between energy and time. If you want to measure the energy of a system very precisely, you need a lot of time to do it. If your measurement is brief, the energy is smeared. And this energy-time uncertainty is the loophole that allows virtual particles to exist. They borrow energy from the vacuum for a moment short enough that the uncertainty principle permits it, and then return it. The stronger the force, the more such virtual exchanges occur. The range of the force is determined by the mass of the carrier particle. Massless carriers like photons produce infinite range forces. Massive carriers like W and Z bosons are confined to incredibly short distances on the order of 10 to the minus 16 centimeters, about 1,000 times smaller than a proton. There is a strange corollary to all of this. If the vacuum is constantly boiling with virtual particles popping in and out of existence, then the vacuum is not empty. It has energy. A lot of it, according to quantum field theory. And here is where cosmology and particle physics collide in a way that should keep physicists up at night. General relativity says that energy, all energy, including vacuum energy, gravitates, so the vacuum energy should curve spacetime. When physicists try to calculate how much vacuum energy quantum field theory predicts, they get a number that is, depending on how you do the calculation, somewhere between 55 and 120 orders of magnitude larger than what we observe. This discrepancy is the largest unexplained number in all of physics. It is called the cosmological constant problem, and no one knows how to solve it. Now, here is where things get genuinely strange on the quantum mechanical side. An electron is not a billiard ball. It is not a tiny sphere of charge. it is a quantum object, and quantum objects are described not by precise positions and velocities, but by wave functions, probability amplitudes spread through space like ripples on a pond. When you measure the electron, you find it somewhere specific. But between measurements, it is genuinely distributed. Not because you do not know where it is, because there is no fact of the matter. This interpretation that the wave function is not a description of our ignorance, but a description of reality, was deeply uncomfortable to many physicists, including Einstein, who spent years trying to prove it wrong. His most famous objection came in 1935 in a paper he wrote with Podolsky and Rosen, known ever since as the EPR paradox. Einstein argued that quantum mechanics must be incomplete, that behind the probabilistic description there must be hidden variables, definite properties that the particles carry, but that our theory cannot access. For 30 years, this was a philosophical debate with no experimental resolution. Then John Bell showed in 1964 that the two views make different quantitative predictions, and experiments starting in the 1970s have confirmed, decisively and repeatedly, that Einstein was wrong. The universe is irreducibly probabilistic. This wave-like nature leads to one of the most astonishing phenomena in physics, quantum tunneling. Imagine a ball rolling toward a hill. If the ball does not have enough energy to climb the hill, classical physics says it turns around and rolls back. Simple. But a quantum particle is not a ball. Part of its wave function extends through the barrier and out the other side. There is a finite probability that the particle will be found on the other side of a barrier it classically could not cross. This is not a trick. It is real. Tunneling drives nuclear fusion in the sun. Protons do not actually have enough energy to overcome their electromagnetic repulsion and collide, but they tunnel through the barrier. Without quantum tunneling, the sun would not burn. You would not be here. Tunneling makes radioactive decay possible. It is the operating principle of the tunnel diode in modern electronics, and it has a striking cosmological implication. The Higgs boson gives our universe a particular kind of vacuum, what physicists call the electroweak vacuum. But in the full theory, there may exist another vacuum state at lower energy than ours. If that is true, our vacuum is metastable. A quantum tunneling event, somewhere in the universe, could nucleate a bubble of true vacuum, and that bubble would expand at the speed of light, transforming the laws of physics inside it. Every particle's mass would change. Chemistry would become impossible. Life, as we know it, would cease. This sounds alarming. The estimated timescale for this event, given our best measurements of the Higgs mass and the top quark mass, is approximately 10 to the power of 800 years. You may safely stop worrying about it. There is another quantum phenomenon that feels even more philosophically uncomfortable than tunneling: entanglement. Suppose a particle decays into two daughter particles, flying off in opposite directions. Conservation laws tell us that certain properties of the pair must sum to zero: charge, spin, whatever is relevant. But quantum mechanics says that until you measure one of the particles, neither of them has a definite value. They are in a superposition, both possibilities simultaneously present. The moment you measure one particle and find it spin up, the other particle instantly becomes spin down, regardless of the distance between them. Across the room, across the galaxy. Instantaneously, Einstein called this spooky action at a distance and was convinced it showed that quantum mechanics was incomplete. Decades of increasingly precise experiments have proven Einstein wrong. The correlations between entangled particles are real, instantaneous, and cannot be explained by any theory in which information travels locally. The universe is, at a fundamental level, non-local in its correlations. This does not allow us to send information faster than light. Any attempt to exploit the correlation to communicate requires a second classical signal to compare results, and that classical signal is limited by the speed of light. But the universe is stranger than our intuitions, and quantum entanglement is perhaps the starkest demonstration of that strangeness. In recent decades, physicists have learned to harness entanglement deliberately. Quantum cryptography uses entangled particles to create encryption keys that cannot be intercepted without detection. Quantum computing uses entangled qubits to perform calculations that would require astronomical time on classical machines. Quantum teleportation, which transfers the complete quantum state of a particle to a distant location using entanglement plus classical communication, has been demonstrated in laboratories. None of this violates relativity. All of it exploits a feature of the universe that Einstein spent his final decades refusing to accept. Now let us turn to the other great revolution of 20th century physics, the one that changed our understanding not of the very small, but of speed and time and space itself. Special relativity arrived from a simple observation. The speed of light is the same for all observers, regardless of their motion. This sounds innocuous. Its consequences are extraordinary. Time passes more slowly for a moving observer. Lengths contract in the direction of motion. The mass, or more precisely the energy of an object, increases as it accelerates. Nothing with mass can reach the speed of light, because the energy required to do so becomes infinite. These are not abstract effects, they are measurable. The GPS satellites orbiting Earth are moving fast enough and sitting in a gravitational field weak enough relative to the ground that general and special relativistic effects shift their clocks by about 38 microseconds per day. 38 microseconds sounds insignificant. At the speed of light, 38 microseconds is 11 kilometers. GPS navigation without relativistic corrections would drift by 11 kilometers every day. Your phone would not know what city you were in. Every time you use navigation, you are relying on Einstein. There is a consequence of special relativity that played a decisive role in the early history of particle physics. Moving clocks run slow, and this means a particle moving at close to the speed of light ages slowly relative to the laboratory. A muon produced in the upper atmosphere, traveling at 99.9% of the speed of light, experiences about 2 microseconds of its own proper time before decaying. In the reference frame of the laboratory of the Earth's surface, that same muon survives for much longer. In its own rest frame, it travels only about 600 meters before decaying. But in the laboratory frame, it travels 10 kilometers and reaches sea level. Muons rain down on us constantly, detected by instruments everywhere. Proof that Einstein's time dilation is not a theoretical curiosity, but a real physical effect. The relativistic energy-momentum relation, where the square of the energy minus the square of the momentum times the speed of light squared equals the square of the mass times the speed of light to the fourth, is one of the most productive equations in the history of science. It tells you that a particle at rest has energy equal to its mass times the speed of light squared. This is the famous E equals mc squared, but that is only the rest energy. A moving particle has additional kinetic energy. And if a particle has zero mass, like a photon, then its energy equals its momentum times the speed of light. It travels at the speed of light always, because it can do nothing else. A massive particle, by contrast, always travels slower than light in any reference frame. But the relation has another consequence that was not immediately appreciated. If you take Dirac's equation, the quantum mechanical equation that describes an electron in a way consistent with special relativity, and solve it, you get two sets of solutions. One set corresponds to electrons with positive energy. The other set corresponds to states with negative energy. What does a negative energy electron mean? Dirac initially interpreted the negative energy states as a sea of filled states, a vacuum occupied by infinitely many electrons. A gap in that sea would appear as a positive energy electron with opposite charge, an anti-electron. Dirac's equation demanded the existence of antimatter before antimatter had been observed. When Carl Anderson found the positron in 1932, Dirac's theory was confirmed in a way that no theorist had fully expected. This is physics at its most beautiful. An equation, written down on mathematical grounds, predicts the existence of a new form of matter. The universe cooperates. With antimatter established as real, another question arose. If the Big Bang produced energy, and if energy converts to particles in particle-antiparticle pairs, one matter particle for every antimatter particle, then why is the universe full of matter? The matter and antimatter should have annihilated completely, leaving a universe containing nothing but radiation. We exist because that annihilation was not quite complete. For every billion antimatter particles, there were 1,000,000,001 matter particles. After annihilation, the billion pairs vanished into photons. The one surplus particle remained. That 1 in a billion excess is us, all the stars, all the galaxies, all the atoms in your body. Everything we see in the universe is the residue of a slight impurity in what should have been perfect symmetry. Where did that impurity come from? The weak force's symmetry violation is part of the answer, but not enough of it. The observed asymmetry between matter and antimatter in the universe is larger than what the standard model can account for. Something we do not yet understand is responsible. This is called the problem of baryogenesis, and it is one of the reasons physicists are certain that the standard model, impressive as it is, cannot be the final word. Let us now trace the history of how we learned any of this, because the path was not elegant. It was messy, accidental, expensive, and full of wrong turns. It was also one of the most extraordinary collaborations in human history. Before accelerators, before controlled experiments, physicists had to work with what the universe gave them, and the universe gave them cosmic rays, particles accelerated to extraordinary energies by distant astrophysical events. Supernovae, the jets of active galactic nuclei, the magnetic fields of rotating neutron stars. These natural projectiles rain down on Earth continuously. Their energies can exceed anything human-built accelerators have achieved by many orders of magnitude. They are the universe's own particle beam. When cosmic ray particles, mostly protons and heavier atomic nuclei, strike the upper atmosphere, they shatter into cascades of secondary particles, pions, muons, electrons, photons, neutrinos, all showering downward. In the 1930s, physicists began dragging ionization chambers and Geiger counters to mountain peaks, sending them up in balloons, lowering them into lakes. They found something unexpected. The more altitude they gained, the more radiation they detected. The source was above them. It was the cosmos itself, bombarding the atmosphere from every direction. The tools of that era were simple by modern standards. Cloud chambers, containers filled with supersaturated vapor, through which a charged particle leaves a trail of droplets, like a contrail across a sky, visible and photographable. The first antiparticle, the positron, was found in a cloud chamber placed in a magnetic field. The field bends the paths of charged particles, electrons curving one way, positrons the other. Anderson photographed a track that curved the wrong way for an electron, with the wrong charge-to-mass ratio for a proton. He checked his equipment. He checked again. The positron was real. Then came the muon in 1937, a particle that looked like an electron but weighed 200 times more. It participated in all the same interactions, electromagnetic and weak, but not strong. It had no business existing. Every rule physicists had established suggested that nature would not simply replicate a particle at a different mass for no reason, and yet it had. The physicist Isidore Rabi, upon learning of the muon's existence, asked the question that has echoed through particle physics ever since: who ordered that? The answer 70 years later is that we still do not fully know. Through the late 1940s and into the 1950s, the flood became a torrent. Cosmic ray experiments kept finding new particles. Strange particles, called strange because they were produced rapidly in a time consistent with the strong force but decayed slowly on a timescale characteristic of the weak force. Something was preventing them from decaying quickly. Physicists invented a new quantum number called strangeness to account for it. Strange particles were produced in pairs, conserving strangeness. But a single strange particle could not decay through the strong force. Strangeness conservation would be violated. It had to decay through the weak force, which does not conserve strangeness, but the weak force is slow. Hence the puzzling combination: fast production, slow decay. The concept of strangeness was the first hint that particles are organized according to deep internal symmetries. Symmetries that constrain which processes are allowed and which are forbidden. In the 1960s, Murray Gell-Mann and George Zweig independently realized that the growing zoo of hadrons, particles made of the strong force stuff, could be organized and explained if they were all composed of smaller entities. Quarks. The proton contains 2 up quarks and 1 down quark. The neutron contains 1 up quark and 2 down quarks. The strange particles contain strange quarks. Every hadron is a combination of quarks and antiquarks, bound by the strong force. This was not immediately accepted. Quarks had fractional electric charge 1/3 and 2/3, which had never been observed, and they could not be extracted from hadrons. The strong force saw to that. For some physicists, quarks were a useful mathematical fiction, a bookkeeping device without physical reality. Then, deep inelastic scattering experiments at Stanford in the late 1960s changed everything. When electrons were fired at protons at high enough energy, they bounced off something hard and point-like inside the proton. The proton was not a featureless blob. It had structure. It contained things. Quarks were real. The picture that emerged from this period is called the Standard Model. It was assembled not by a single genius, but by many people over roughly 3 decades through a combination of theoretical insight and brutal experimental work. Its final elements, the W and Z bosons, the gluon, the top quark, and ultimately the Higgs boson, were confirmed one by one between 1973 and 2012. The confirmation of the Higgs at the Large Hadron Collider was the last piece of a puzzle that had been mostly assembled for 40 years. Physicists celebrated and then asked, "What now?" There is nothing left to find in the Standard Model. Every particle it predicts has been found. Every force it describes has been measured. The question is what lies beyond it, and here the theory is silent. One of the most productive ideas about what might lie beyond is called supersymmetry. The Standard Model contains 2 types of particles: fermions, which are the matter particles, and bosons, which carry the forces. Supersymmetry postulates a deep symmetry between these 2 types, that every fermion has a bosonic partner and every boson has a fermionic partner. This symmetry, if it exists, would solve several of the most nagging problems in the Standard Model simultaneously. It would explain why the Higgs boson's mass is stable against quantum corrections, because the corrections from superpartners would exactly cancel the corrections from ordinary particles. It would provide a natural candidate for dark matter, the lightest superpartner, stable because it cannot decay into anything lighter within its own symmetry sector. And it would bring the strengths of the strong, weak, and electromagnetic forces into precise alignment at a single very high energy, suggesting that all 3 might be different facets of a single unified force. Supersymmetry is mathematically elegant. It is theoretically well motivated, and it has not been found. The Large Hadron Collider has now searched thoroughly through the energy ranges where the simplest supersymmetric theories predicted superpartners should appear. They are not there. Either supersymmetry does not exist, or it is realized in a form more complex and subtle than theorists preferred. The experiments continue, and the energy frontier will eventually be extended by new machines, but the easy versions of supersymmetry are ruled out. Let us return now to the particles that behave as though they were made for frustrating physicists: neutrinos. Neutrinos are among the most abundant particles in the universe. At this moment, approximately 65 billion solar neutrinos are passing through every square centimeter of your body every second. Every second. You cannot feel them. They interact only through the weak force and gravity, and the weak force is extremely weak at low energies. For a solar neutrino, the mean free path, the average distance it travels before interacting, is several light-years of solid lead. The entire Earth is essentially transparent to them. This makes neutrinos extraordinary messengers. While the light we receive from the sun comes from its surface, photons that took tens of thousands of years to diffuse outward from the core, neutrinos stream directly from the nuclear reactions in the sun's center, arriving at Earth in about 8 minutes. Detecting solar neutrinos means looking at what the sun is doing right now, not what it was doing when photons from its core were first emitted. For decades, the solar neutrino problem haunted physics. Theory predicted a certain flux of electron neutrinos from the sun's fusion chain. Experiments consistently measured fewer, about a third of what was expected. Either our model of the sun was wrong, or our model of neutrinos was wrong. The answer turned out to be something nobody had fully anticipated. Neutrinos change type in flight. An electron neutrino produced in the sun's core can arrive at Earth as a muon neutrino or a tau neutrino. The neutrino exists during its journey as a quantum superposition of all three types simultaneously, oscillating between them as it propagates. The experiments were only sensitive to electron neutrinos. They were missing the 2/3 that had converted to other flavors. This phenomenon, neutrino oscillation, is only possible if neutrinos have mass. The original standard model assumed they were massless. The discovery that they are not, confirmed in 1998 from observations of atmospheric neutrinos and in 2001 from the SNO experiment in Canada, earned Nobel Prizes in 2015. It was the first confirmed deviation from the standard model in particle physics. The experiments that proved this are marvels of engineering patience. In a mine in Japan, a chamber the size of a 10-story building is filled with 50,000 tons of ultrapure water and lined with 11,000 photomultiplier tubes. When a neutrino occasionally interacts with a water molecule and produces a charged particle moving faster than light travels through water, not faster than light in vacuum, but faster than light moves through water, which is slower, it emits a cone of blue Cherenkov radiation. The photomultiplier tubes detect the flash, the direction, timing, and pattern of the flash, tell you the direction and energy of the incoming neutrino. Super Kamiokande detects a few thousand solar neutrino events per year from the 65 trillion that pass through its water volume every second. The rest pass through as if the detector were not there. Other experiments used different materials. Some used gallium, a metal that is liquid at room temperature, because gallium nuclei can capture electron neutrinos and convert to germanium in a reaction with a very low energy threshold, sensitive to the bulk of the solar neutrino flux. The germanium is chemically extracted, counted, and the neutrino rate inferred. Every few months, the entire target, hundreds of tons of liquid gallium, is processed to extract a few dozen germanium atoms. The patience required is almost incomprehensible. Deep under Lake Baikal on the ice in winter, teams from the Budker Institute drill holes through 1.5 meters of ice and lower strings of photomultiplier tubes to depths of 1.5 kilometers below the surface. They are building a cubic kilometer neutrino telescope using the lake itself as the detection medium. Similar experiments exist under the Antarctic ice. These instruments are not searching for solar neutrinos, but for cosmic neutrinos, the highest energy neutrinos in the universe, produced by the astrophysical accelerators that also generate cosmic rays. By mapping where in the sky these neutrinos come from, physicists can identify the most extreme and violent objects in the universe. The places that accelerate particles to energies our machines can never match. Now let us consider the other thing the universe is full of that we cannot see and do not understand: dark matter. The evidence for it is overwhelming and comes from multiple independent sources. The rotation curves of galaxies, stars in the outer regions of spiral galaxies orbit at speeds that should make them fly apart. If the only mass present were the visible stars and gas, they do not fly apart. There must be additional invisible mass. The dynamics of galaxy clusters. Clusters of hundreds of galaxies move relative to each other at speeds that imply far more gravitational mass than the visible galaxies contain. Gravitational lensing, the bending of light from distant objects by intervening mass, reveals mass distributions that extend far beyond any visible matter. The cosmic microwave background. The pattern of fluctuations in the afterglow of the Big Bang encodes the ratio of ordinary matter to dark energy, and the numbers are precise and consistent. Dark matter is not a speculation. It is an inference as solid as any in astrophysics. What dark matter is, we do not know. The candidates are numerous. Some are WIMPs, weakly interacting massive particles, hypothetical particles with masses around 100 times the proton mass that interact through the weak force and gravity. WIMPs arise naturally in supersymmetric theories, and for decades they were the favored candidate. Large underground detectors, cooled to millikelvin temperatures to reduce noise, have searched for the rare scattering events that would occur if WIMPs passed through ordinary matter. So far, nothing. The sensitivity of these experiments has improved by many orders of magnitude over 2 decades, and the most popular WIMP models are now severely constrained. Other candidates, axions, ultralight particles motivated by a different problem in the standard model, predicted to have masses roughly 100 million times lighter than the electron. Sterile neutrinos, hypothetical additional neutrino flavors that do not participate in weak interactions at all, communicating with ordinary matter only through gravity and tiny mixings. Primordial black holes. Black holes formed in the early universe before any stars existed. All of these remain possible. None has been confirmed. If dark matter consists of fermions, the Pauli exclusion principle places a sharp constraint on its properties. You cannot pack fermions too densely without violating the exclusion principle. Dark matter halos around dwarf galaxies have a minimum density consistent with this constraint, and from observations of dwarf galaxy halos, you can derive a lower bound on the mass of any fermionic dark matter candidate. The result, fermionic dark matter must be heavier than about 1 keV in energy units, roughly 2,000 times the mass of an electron neutrino. This rules out light sterile neutrinos as the dominant dark matter component. Bosonic dark matter carries no such constraint. The lightest bosonic dark matter candidates, sometimes called fuzzy dark matter, are so light that their quantum wave function extends across an entire galaxy. A single particle in a halo of fuzzy dark matter would be smeared across tens of thousands of light years. The halo would behave as a single quantum object. This sounds absurd, but it makes specific, testable predictions about the structure of galaxies at small scales, and current observations are beginning to discriminate between these models. Now, let us step back and ask the larger question that connects all of this. Where does physics stand, and where does it go? The standard model is complete. It is also insufficient. It cannot be the final theory of nature because it fails to incorporate gravity, fails to explain dark matter, fails to explain the matter-antimatter asymmetry, and fails to explain the values of its own parameters. Physicists know this. The question is which of the many proposed extensions is correct, and experimental guidance has been stubbornly scarce. The Large Hadron Collider found the Higgs boson in 2012. This was the capstone of a theoretical edifice built over 50 years. Since then, the LHC has continued operating at higher energies and luminosities, collecting data at a rate that would have seemed fantastical to the physicists of the 1930s, and it has found nothing beyond the standard model. Not a single superpartner, not a single additional Higgs boson, not a hint of extra dimensions. This is not the result theorists expected, and it has prompted serious reflection about whether the theoretical frameworks that dominated post-standard model thinking, supersymmetry, extra dimensions, grand unification, are actually realized in nature. Some physicists believe the LHC simply has not yet reached the relevant energies. New machines are proposed, the Future Circular Collider at CERN, a 100-kilometer ring that would collide electrons and positrons, then protons and protons, at energies several times higher than the LHC. The Circular Electron-Positron Collider proposed in China, the International Linear Collider in Japan, designed to produce Higgs bosons in enormous numbers and measure their properties with precision and order of magnitude beyond what is currently possible. These machines would not be completed for decades, and they would cost tens of billions of dollars. Whether the investment is justified, whether the physics they could discover is worth the cost, is a genuine debate, not just a scientific one, but a political and social one. Meanwhile, observational cosmology has become a precision science that particle physics could learn from. The Planck satellite measured the cosmic microwave background to extraordinary accuracy, pinning down the densities of ordinary matter, and dark energy. Gravitational wave detectors, LIGO in the United States, Virgo in Italy, have opened an entirely new observational window on the universe, detecting mergers of black holes and neutron stars that were previously invisible. Future gravitational wave detectors, including the space-based LISA observatory and next-generation ground-based instruments, will detect gravitational waves from sources throughout cosmic history, including possibly from the phase transitions of the early universe that are connected to the physics of the Higgs field. And there are questions that none of these instruments can directly answer because they lie at energy scales forever inaccessible to any machine built from ordinary matter. The Planck scale, where quantum gravity becomes important, corresponds to energies 17 orders of magnitude beyond the LHC. No particle accelerator could ever reach it. The only laboratory where Planck scale physics operated was the universe itself, in the first tiny fraction of a second after the Big Bang. This is where the problem of quantum gravity stops being abstract and becomes urgent. General relativity describes the universe's expansion, the formation of structure, the behavior of black holes, all magnificently well. But it breaks down at the singularities inside black holes and at the beginning of the universe. These breakdowns are not technical failures. They are signals that the theory is missing something fundamental. At a singularity, the curvature of space-time becomes formally infinite, and the theory produces results with no physical meaning. Either there are no singularities in nature. They are an artifact of the classical description that a quantum theory of gravity would resolve, or something genuinely inexplicable happens at those points. Most physicists believe the former. General relativity is wrong inside black holes, not because its equations are badly set up, but because it is a classical theory applied where quantum mechanics must dominate. String theory was for decades the leading candidate for quantum gravity. Its central idea, what we call point particles, are actually tiny vibrating strings, and the different vibration modes of a string correspond to different particles. One of those modes inevitably corresponds to a spin-2 massless particle, which is precisely the graviton. String theory thus contains quantum gravity automatically, without any of the mathematical pathologies that plague attempts to quantize gravity directly. Its other remarkable feature is that it requires extra spatial dimensions beyond the three we experience, curled up so tightly at every point in space that they are invisible at accessible energies. If the extra dimensions are large enough, they could in principle be detected at the LHC. They were not. The bounds on large extra dimensions are now severe. String theory has not made a single prediction that has been experimentally confirmed. This is a serious criticism. Its defenders argue that the theory is so mathematically rich that it is not yet understood well enough to make sharp experimental predictions, that we are still discovering the implications of the theory, and that its predictions may not be accessible at the energy scales we can probe. This is a reasonable defense, But it is also, in the eyes of skeptics, an unfalsifiable one. A competing approach, loop quantum gravity, abandons strings entirely and tries to quantize space-time itself, to turn the geometry of space and time into quantum objects with discrete granular structure. In this picture, there is a minimum length in nature, roughly the Planck length, below which the concept of space loses meaning. Loop quantum gravity has had some successes in cosmology, particularly in resolving the Big Bang singularity, replacing it with a bounce from a previous contracting phase, but it has not yet made contact with the particle physics of the Standard Model. The honest answer is that we do not know which approach is right, or whether the correct approach has yet been invented. What we do know is that the universe is described at its deepest level by rules that are nothing like our everyday intuitions, particles that do not have definite properties until they are measured, forces that arise from the exchange of virtual quanta borrowed from the vacuum, matter made of fermions that refuse to share the same state, giving rise to the entire complexity of chemistry and biology, antimatter partners for every particle, symmetries that are broken by the weak force in ways that made the universe possible, dark matter that we can see only through the shadows it casts in gravity. Gravity itself, which shapes everything on the largest scales, but which stubbornly resists incorporation into the quantum framework that governs everything else. This is not a tidy picture. It is not the picture of a subject that has reached its end. It is the picture of a subject in the middle of something, in the middle of a journey that began with Rutherford firing alpha particles at gold foil, that passed through the cloud chambers of the cosmic ray era, through the massive accelerators of the mid-20th century, through the precision measurements of the Standard Model and its ultimate confirmation. The journey has reached a plateau. The instruments are larger, the detectors more sensitive, the theories more elaborate, and the new discoveries have stopped, at least for now, at least at accessible energies. Historically, this is not unusual. There was a plateau before quantum mechanics. The experiments of the late 19th century, blackbody radiation, the photoelectric effect, atomic spectra, refused to be explained by the tools available. The resolution, when it came, did not just add new facts, it replaced the conceptual foundations. The notions of trajectory, of determinism, of the separability of observer and observed, all of these were overhauled. The mathematics required had already been invented, but its application to physics was genuinely new. Something like that may be ahead. Perhaps the framework needed to unite quantum mechanics and general relativity requires not just new mathematics, but new concepts, concepts for which we do not yet have names, because we do not yet understand the problem clearly enough to name what is missing. Perhaps the dark matter problem has a resolution that will seem obvious in retrospect, as so many solutions do. Perhaps the matter-antimatter asymmetry is the signal of a force we have not yet imagined. 100 years ago, Bohr and Heisenberg were arguing about the meaning of the wave function in Copenhagen. Einstein was insisting that God does not play dice. Dirac was finding antimatter hidden in an equation. Pauli was deducing the existence of the neutrino from a bookkeeping problem in nuclear decay. None of them knew where they were headed. They were following the experiments, following the mathematics, following the questions. That is still how physics works. The questions are different now. The instruments are incomparably more powerful. The community is global, international, and spans thousands of researchers rather than dozens, but the fundamental method is unchanged. You measure what you can. You build theories to explain it. You find where the theories fail. You rebuild. The universe is under no obligation to make sense on human terms, but it has consistently agreed to reveal itself to those patient and precise enough to ask.